Okay, to begin with today's proceedings, we left off, we were just about to do example 6.5, which involves what's known as an Atwood machine. An Atwood machine is really just a pulley with a rope over it with holding two objects of different masses. And you can do various experiments with involving acceleration due to one mass being greater than the other, and tensions in the lines and all kinds of things like that. So in this example here, we've got mass 1 and mass 2 over with the rope over the pulley. You can assume that the rope has no mass and that the pulley is frictionless for the sake of simplicity, because if we didn't make those assumptions, things would get really complicated really fast. And they're close. Those assumptions are close enough to reality that we can get at least a good approximation of what the situation would be, even with those assumptions in place. And let's see, mass 1 is 2 kilograms and mass 2 is 4 kilograms. And the question is, if mass 2 is released, what is the acceleration? You've been holding mass 2 up and you want to release it. And also, what is the tension in the string? And looking at the situation, we've got two bodies that we need to be concerned with, the first block and the second block. And for the first block, you've got a couple of different forces on it. And one of them would be the weight of block number 1, which pulls downward. And the other would be the tension in the line pulling upward. For block number 2, we have similar forces. We have the weight of block number 2 pulling downward and the tension in the line pulling upward on block number 2. Basically, if you're holding block number 2, which is the heavier block, and you let go of it, it's going to accelerate downward because it's heavier. That means that mass 2 is going to accelerate upward at the same rate, assuming that the line doesn't stretch. And for simplicity, we basically have to assume that the line doesn't stretch. Okay, and since the rates are the same, we can say that acceleration for block 1 is equal to the negative of the acceleration for block 2, because if we're taking the direction into account, then upward would be positive and downward would be negative. And in terms of the magnitude of the number, we're just going to call that A. So A1 will be equal to A, and negative A2 will also be A. And what we want to do is look at the forces that are in play on these two objects, and particularly the forces in the Y direction, the up and down direction. There is no net force on either of the objects in the X direction because they're not moving side to side. They're only moving up and down. So we're concerned about the net force in the Y direction on block 1, or M1, that is the block with mass 1, and also on block 2, that is the block with mass 2. So for block 1, the sum total of all of the forces in the Y direction would be equal to the mass of block 1 times its acceleration, of course, because F equals ma. But in terms of our diagram here, the total of all of the forces on block 1 in the Y direction would be the tension in the line minus the weight. Weight is mass times gravity, so weight of block 1 would be mass of block 1 times g, or gravity. Okay. And for block 2, we would have the sum total of all of the forces in the Y direction would be equal to the negative of m times a. That's because a for block 2 is negative. So it's negative m2a, because again, force equals ma, and for block 2, the mass is m2, and the acceleration is negative, so that's where the negative sign came from. But for block 2, the summation of all of the forces from our free body diagram here is the tension in the line minus the weight. the weight of block 2 is mass 2 times G. Okay. Oh, sorry. And to solve for the unknown tension, we can remember the tension in the line for the two objects is the same. So this T over here for block 2 is the same as this T over here for block 1. So in other words, all we have to do to find T is to put these two equations together. We know that the summation of all of the forces on block 1 in the y direction should be minus the summation of all of the forces on block 2 in the y direction. Well, we can actually take these two expressions and equate them to each other. So using the terms that involve tension and mass and gravity, for block 1, you would have the tension minus mass of block 1 times G minus the tension, the summation of forces for block 2, which in those terms would be the tension minus the mass of block 2 times G. And that would be equal to, in terms of mass and acceleration, for block 1, that's m1 times a. And for block 2, it's negative m2 times a. Okay, so you work out some of the math here. We end up with ultimately m2 minus m1 times g is equal to m1 plus m2 times acceleration. Because minus a negative is like adding a positive. And for this, all you have to do is solve for acceleration. So acceleration is going to be mass 2 minus mass 1 over mass 1 plus mass 2 times g. Since we have numbers in this case, we can put the numbers in. Mass 2 is 4 kilograms minus mass 1, which is 2 kilograms, over mass 1 plus mass 2, that's 4 plus 2 kilograms times 9.8 meters per second squared. And that gives us 3.27 meters per second squared as the acceleration. Okay, we have the acceleration now. For part B, we want to go on and find the tension. Now that we know the acceleration, that's going to be a lot easier. For block 1, using block 1, anyway, we have from the previous example that the summation of all of the forces in the y direction on block 1 is equal to mass of block 1. Oops, sorry, that wasn't on screen. Summation of all of the forces on block 1 in the y direction is equal to the mass of block 1 times acceleration, which is also equal to the tension minus mass 1 times g. Well, we know all of this stuff here except for the tension. So you set those two equal to each other. You solve for the tension. Tension is mass 1 times acceleration plus mass 1 times g. If you want to, you can factor out mass 1 and have mass 1 times a plus g if you want, or you can just stick the numbers in. So for block 1, the mass is 2 kilograms times acceleration, which is 3.27 meters per second squared, plus 2 kilograms times 9.8 meters per second squared. When you add all of that up, you get 26.1 newtons. Since the tension is the same in both parts of the line, the part attached to block 1 and the part attached to block 2, that's really the only answer you need. You don't have to find out the tension anywhere else. But just to demonstrate that the tension really is equal in all parts of the line, I'm going to go on and solve for the tension using the data from block 2. Using block 2, we have the summation of all of the forces in the y direction on block 2 would be equal to negative mass 2 times acceleration, which we saw in the last part, which is also equal to the tension minus mass 2 times g. Well, again, we can solve for the tension here. That ends up being m2g minus m2a. And m2 is 4 kilograms times 9.8 meters per second squared, minus 4 kilograms times the acceleration, which is 3.27. And when you work that out, you get 26.1. So we've basically proven that the tension is the same everywhere on the line. So Newton's laws of motion and kinematics apply to a lot of different situations involving many types of forces and many types of motion. And before we can apply them, we just really have to sort of think about the situation and analyze what forces are involved and what equations might need to be used to find what we want to find. Kind of an example of that, applying it to a situation that's a little more out there and that you might not immediately think of Newton's laws in connection with, would be what force does a soccer player, or anybody, for instance, running, have to exert to reach top speed? So what we've got here is a player who starts at rest, that is, standing still, and accelerates forward to a velocity of 8 meters per second within 2.5 seconds. So the question is, what is the average acceleration? That's pretty easy. But B is, what is the average force that the ground exerts in a forward direction on the player in order to achieve this acceleration? We know from the action-reaction forces that when you run forward, you're exerting a backwards force on the ground. And in return, the ground exerts a forward force on you, and that's what actually moves you forward. It's forces from outside the system that are imposed on the system that actually, that actually cause movement in the system. So it's the ground pushing forward on you that causes the movement. Let's see, the player's mass is 70 kilograms, and at these kinds of speeds, air resistance can be ignored. So for part A, what is the acceleration? Well, we know the final velocity and the initial velocity. The initial velocity was 0 because it says the player starts at rest, and the final velocity is 8 meters per second. And we know the time period over which that happened, 2.5 seconds. So the acceleration, average acceleration for the time period, is just the change in velocity over the change in time. The change in velocity is 8 meters per second, because 8 minus 0 is 8. And delta t is 2.5 seconds. So we get 3.20 meters per second squared. That's the average acceleration over this time period. All right. Now, as for the force that the ground applies to the player in order to get the player to move forward, the force, again, of the ground on the player is forward, and that's a reaction force to the player, to the player's backward force that the player exerts on the ground with his feet. And that's also equal to the net external force on the player. Again, assuming no air resistance. And so what we know the player's average acceleration and mass. So we know that the net force on the player is just mass times acceleration, which is going to be 70 kilograms times 3.20 meters per second squared, which would be 224 newtons. And that is the force that the ground exerts on the player. Because again, the only outside force on the player, other than wind resistance, is going to be the force of the ground pushing the player forward. So we know the magnitude right away, 224 newtons. Okay, so that was actually easier than it seemed. You just have to sort of understand the forces involved and how they relate to each other. Another example in 6.7 is the example of the forces on a model helicopter. We've got a model helicopter with a mass of 1.5 kilograms, and it has a velocity that's given by a vector equation, 5 times unit vector j meters per second at time 0. Okay, at time 0. It accelerates at a constant rate for 2 seconds, after which it has a velocity of 6 times unit vector I plus 12 times unit vector j meters per second. So what is the magnitude of the resultant force acting on the helicopter during the acceleration, during the 2-second interval? Okay, first we have to find out the average acceleration for the period, and that is delta V over delta T. Delta V, remember the velocity was given in vector terms, so it's just not just the matter of subtracting numbers. We have to do a vector subtraction here. So for delta T, it's going to be the final velocity, which is 6I plus 12J, minus the original velocity, which is 5J. And we sort of pair up the J terms and subtract them. And so it ends up being, delta V ends up being 6I plus 7J meters per second. That's the change in velocity during this 2-second period. Acceleration, or average acceleration for that 2-second period, is delta V over delta T. Delta V we just found, 6I plus 7J meters per second. Delta T is 2 seconds. And you can divide a vector by a scalar, 2 seconds being a scalar, because that's really just the same as multiplying the vector by 1 over the scalar, which is itself a scalar. So you can do that. And so you just essentially divide the coefficients by 2 for what we had for the velocity. And that's going to be 3I plus 3.5J. But because of the units of seconds on the bottom, that's going to be meters per second squared. So that's the acceleration. 3I plus 3.5J. Okay. The summation of all of the forces, again, is going, or the net force, in other words, is going to be 6I, or sorry, it's going to be mass times acceleration. The mass of the model helicopter is 1.5 kilograms. The acceleration we now know is 3I plus 3.5J meters per second squared. And again, you can take this vector equation, 3I plus 3.5J, and you can multiply it by a scalar. 1.5 kilograms is a scalar. So you multiply each of the coefficients by 1.5 and add the kilograms to the units. So we end up with 4.5I plus 5.25J kilogram meters squared per second squared, or in other words, newtons. Okay, so that's the net force on the equation, or on the equation for the net force on the helicopter. The question was asking for the magnitude of the resultant force. It didn't ask for the direction, but I might as well throw that in as a bonus. Anyway, the magnitude is going to be the square root of the x term squared plus the y term squared. So that's the square root of 4.5 squared plus 5.25 squared, which comes out to be 6.91 newtons in the direction that the force is actually acting. Okay. And that direction, even though the original question didn't ask for it, that direction would be inverse tangent of the y term over the x term. So that's inverse tangent of 5.25 over 4.5, which is 49.4 degrees. Okay, so we found that too. So far, not too bad. There is an example that gets a little more complicated, and that is the next example where we have an airport baggage tractor that is pulling 2 carts full of luggage behind it. And we're in part of this, we're basically trying to figure out what the speed of the agglomeration of vehicles is. And that's not so difficult. But in part B, we're going to be trying to find the tension in the line between the tractor and the first baggage car. Okay, so we have some information that's given to us in the question. It's an airport baggage tractor that's pulling 2 carts full of luggage, and they're connected by a flexible cable, and a cable that doesn't stretch though, and whose weight can be ignored. And the tractor's mass is 650 kilograms. Baggage cart A has a mass of 250 kilograms, and baggage cart B has a mass of 150 kilograms. The tractor engine is the thing that actually accelerates the system. And it does this over a 3-second period. And so question A is, if the driving force of the tractor's engine is given by F equals 820 T times, or newtons, that is the driving force of the tractor is time dependent. What is the speed after 3 seconds? Okay. Now remember, you can't just put 3 seconds in here because this is the equation for force, not for speed. And part B is, what is the horizontal force acting on the connecting cable between the tractor and cart A? In other words, what's the tension in the line? So for part A, you can draw a free body diagram where we have the first dot representing the tractor that's pulling the baggage carts, and the second dot would be cart A, and the second or third dot would be cart B. For each of these bodies, you have up and down forces involved. You have the weight of the tractor or the baggage cart A or baggage cart B pressing downward, and you have the normal force of the ground pressing up on them, which is equal to the weight, equal in magnitude, of course, opposite in direction. So in other words, the vertical forces cancel out. And you can tell that because the cart or the baggage caravan is accelerating in the X direction, not in the Y direction. It's not rising or falling. In the horizontal direction, the only force that is acting on this baggage caravan basically would be the force of the tractor. And so it's Ft, that is the force of the tractor, that causes acceleration. And all of the motion is horizontal because the vertical forces cancel out. We'll come back to this diagram for part B in a moment. For part A, if the equation for the forces on the tractor is given by 820 times T, that must be the summation of the forces in the X direction, because as we already saw, all of the forces in the Y direction cancel out. And so summation of forces in the X direction is 820 times T, and that is also mass times acceleration. In this case, we're looking for the mass of the entire system because all of these tractor and the baggage carts are all connected to each other and they're all moving as one. And that would be times acceleration in the X direction, again, because there is no acceleration in the Y direction. So we have 820 T equals the mass of the system, which is 650 plus 250 plus 150 kilograms, times acceleration in the X direction. So that's 820 T is equal to a total of 1,050 kilograms times acceleration in the X direction. And so you can solve for A in the acceleration in the X direction, and that ends up being 820 over 10 T over 1050, which is 0.7810 T. That's the acceleration in terms of time. Okay, acceleration, though, as we know, is the derivative of velocity. So velocity would be the derivative, or would be rather the integral of acceleration. So velocity in the x direction would be the integral of acceleration in the x direction with respect to time. And we're doing this from time 0 to 3 seconds. Another way of writing this is Vx equals the integral from 3 seconds down to 0 seconds of ax dt. And if we're going to take the the integral of acceleration with respect to time, that's what dt means, then we're going to have to get acceleration in terms of time, which we just did. So that's the integral from 3 seconds down to 0 seconds of 0.7810 t times dt. And that is 0.7810 over 2 times t squared. Because remember, when you're taking an integral, you take the variable and raise its power by 1, and then divide the coefficient by that number. So t in the original integral is to the first power. So you change that to t squared, and then you divide the coefficient by 2. So 0.7810 divided by 2 times t squared. And that comes out to 0.3905 t squared from t equals 0 to t equals 3. So what we do is we take the final minus initial. That's 0.3905 times 3 seconds squared minus 0.3905 times 0 seconds squared, which of course is 0. And that ends up being 3.515 meters per second. So that was a bit of a way to go for that, but we succeeded. We did find the velocity. Okay. All right. Okay, that's a little over the limit for this segment of the video. I'm going to do part B when we come back for the second segment. So hope I'm not leaving in too much suspense.